Okay, we are on to derivatives of exponential functions, part 2, still in section 4.4. Just to put it into perspective for you guys, all we've done so far is we've established what's our rule for finding the derivative of any function in the form e to some power. So we started with e to the x, but then we changed it to e to any power. I can handle it because I can use my chain rule. So in the world of exponential functions, that is really just one tiny, tiny, tiny part of what I really have going on, because I could really have any base, not just e. I could really have any base to a power. So our goal is to figure out how can we actually find the derivative. Do we have a rule for some other base besides e to a power? So this is really my goal here, is what can I say that that's equal to derivative of a to the x? Okay, we're going to have to take a quick little trip back in time so that we can look at something from pre-calculus, some rules when it comes to actually logs and exponentials and how they relate to each other. So keep that thought, but let's go back in time for just a minute. I want us to look at the function, or the expression rather, e to the x times natural log of a. And if I just ask you to simplify this function, or this expression, what could we do to simplify this? We should be remembering a power, whether or not we would think to do it here. See if you can agree with this. A rule that I can take that number, and sometimes we went the other way as well, but I can take that number in front of a log expression, and I can actually make that the power. So I'm going to rewrite this as e to the natural log of a to the power of x. Okay, you don't have to understand why I'm doing that yet, but just make sure you can follow and agree with that. And now if we observe, hopefully you can realize that e to some power of where I've got a exponential, or where I've got a log expression, if that base, and the base of my natural log is definitely e, if that base is the same as the base of my expression, those cancel out, and I actually end up with getting a very simple a to the x, because e to the natural log cancels out. Okay, that's what I need you to remember from pre-calculus, so that we can make this jump that e to the x natural log of a that I had right here is equal to a to the x. We will be coming back to that, and we're going to kind of skip over that middle step that I just showed you. Okay, so let's go back to my original question of how do I find the derivative of this function, a to the x. And I'm going to propose, based on what I just said, that I make this substitution that y equals a to the x, we write as y equals e to the x times natural log of a. That was supposed to be an L. Let's fix that. X times natural log of a. Okay, so that's based on this equation, or that derivation that we made right there. If I can get there, now I'm just applying what I did in the beginning of this section, which was how do I take the derivative of e to some power? So recall that our derivative rule is dy dx equals e to the u times the natural log of, I'm sorry, not natural log, e to the u times du dx. Okay, and that's all I'm going to do here. So I'm going to establish that my u in this problem is x times natural log of a. Possibly looks scarier than anything we did in the previous examples, but let's actually look at that and think about what we have. We're going to need the derivative of u with respect to x, and the derivative of u with respect to x is natural log of a. We got to figure out what's going on there. A is just some constant. Remember, we have some number to a power x, and we're calling that number base a. So as weird as this looks, our natural log of a is really just a constant. Maybe it'd be better to think of that as natural log of a times x, and it's the same as if it was 5x or negative 2x or 20x. Your derivative is just going to be that number. So my derivative of u with respect to x is actually just the natural log of a. So if I come over here and I go ahead and figure out what I have going on here, dy dx equals e to the u times du dx. E to the u is what I had for my function, e to the x natural log of a, times my du dx, and this is where I'm going to put it in, right here, times the natural log of a. So that's not looking too bad, but I have one other thought. Can we actually make this better? Can we go ahead and make a substitution here based on, again, this original thought, this original question that we considered? A to the x, now I'm going to go backwards, a to the x is equal to e to the x natural log of a. So if I can use this substitution, I have e to the x natural log of a, and I'm going to replace all of that with a to the x, get rid of the e that I inserted in there to allow me to take the derivative. But remember, I started with a to the x right here. And I'm going to say that my derivative is really just a to the x times natural log of a. And that's a pretty nice rule for us. Now, if we think about it, we started with a function a to the x. So that's some base to a power. Derivative is really that base to the power. Hey, that looks a lot like e to the x, right? If it was derivative of e to the x, it was e to the x, but now it's a to the x, but I've got to multiply it by the natural log of the base, whatever my base is. Okay, we're going to look at some examples, and I know that'll make it easier, but I wanted you to see somewhat where it came from. So let's formalize this. You're going to have rules 3 and 4 here, because the first two were dealing with when I had a base of e. So rule 3, technically, for this section is when I have a derivative of some base to a power, it's that base to the power times the natural log of that base. And then let's generalize for when I have a to some power u, where my power is no longer just a simple x, but a function. And if you've been following what we've been doing with the chain rule, we should be realizing that that's going to be a to the u times times natural log of a. Nothing changes there, but now that I have a u introduced into it, I'm going to follow that times du dx, and that's my chain rule kicking in. Okay, so those are my new rules. Let's go ahead and look at some examples. And if you lost me in the proof, just jot down those rules. Let's see if you can follow as we do some examples. So first example for this new rule, these new rules that I have, let's go ahead and look at something like, so I think this is really example 6 overall. Y equals, let's suppose I have 8 as my base, so I've got 8 to the x power. So just a quick review, my derivative rule tells me that if I have a to some power and I want to take the derivative of that, so what we just wrote down, it's a to that power times natural log of a. So in this question right here, I'm thinking that my a is 8 is what I'm thinking, because that's my base. So we've got a is 8. And I'm just going to go ahead and substitute in for my rule. So my dy dx is going to be a to a power. So right now I'm on this part, and my a was 8, so it's going to be 8 to the x. Again, that's directly what I had for my function. You're going to notice that, just like we had e to the x, but because it's not a base e, I'm going to have to follow it by the natural log of a. So natural log of a is natural log of 8. And that's it. If you want to rearrange it, you can. I don't think there's really a preference there in terms of what part's first. 8 to the x times natural log of 8. I'm good with leaving it just like that. Okay, let's try another one. So let's suppose that my function looks more like this. Y equals x cubed plus 3 to the x. And I want to take the derivative of that. So I do have two parts here. I've got a sum of two functions. So good news is that I'm not going to have to do the product rule. I'm going to have to think about the two functions. And I intentionally, yes, made these look similar but different. Of course, they both have a 3, but what's the difference? First function we should be recognizing is good old power rule. That's from way back when we first started derivatives. Don't get confused. I know we've got an x and a 3, but that's not an exponential. That's a power rule problem. So my derivative there is going to be 3x squared, and nothing more complicated than that. Now let's deal with the second part where I've got a number to a variable power rather than a variable to a number power. And here's where I got to apply what we just talked about. So again, I'm going back to my rule up here, and in this case my a is 3 because that's my base. So I've got 3 to the x, a is 3, which means that I'm going to end up with derivative of 3 to the x times natural log of 3. And again, nothing much that I need to do there. And again, I don't need to use the chain rule because I have a simple power of x. So let's leave that one alone. And let's look at one where we are going to need the chain rule. So what if I have something like y equals 3? We'll keep the base 3, but make it look different. So now my exponent is something crazy looking, definitely not just a simple x. So y equals 3 to the cotangent x power. That is an ugly function. So derivative rule tells me, hey, if I want to take the derivative of something with respect to x and it's in the form a to some power u, then I'm going to do a to that power times natural log of a times, I'm going to have to follow that by du dx, since I'm finding the derivative with respect to x and I've got this power u. Okay, so that's my general rule that I'm going to follow. Let's establish that we're going to have our u be this function cotangent x. So my du dx derivative with respect to x of cotangent x is negative cosecant squared x. Okay, and now let's go ahead and apply my rule. So my dy dx in this case is going to be a to the u. Well, that's going to be 3 to the u, since I'm thinking of this as u, that's what I've defined it as, times the natural log of my base 3 times my du dx, which is negative cosecant squared of x. Doesn't want to move though. So the only way I can simplify that is I can go ahead and substitute in my u, and I'm going to bring this negative out front that I have right here. So let's put that in front. Negative 3 to the power of u, which is cotangent x, I'm substituting u in for that, times the natural log of 3 times the cosecant squared x. And that's the final answer there. Okay, so good news is that it doesn't look like we're going to have to do too much substituting or too much simplifying at the end, but you're going to end up with some maybe what you would consider ugly answers when you go through this process. Okay, I think that's good enough that you can try a few on your own now.